Today's episode was recorded in Brooklyn, New York on November 20th, 2024. Please be sure to check out our other episodes, including one with Jack Antonoff and an MIT physicist on the topic of time perception. Don't forget to click subscribe, and please rate the show on your favorite podcast platform. This is Sing for Science Labs. I'm your host, Matt White. Each episode in this series brings together artists and scientists to explore one topic of shared interest. Today's topic is plasma physics, and our guests are French musician Rahim Redcar from Christine and the Queens and Italian astrophysicist Matteo Cantiello. How did I do on the pronunciation there?
It's great.
Thanks. Rahim has been releasing music as Christine and the Queens since 2014 to critical acclaim and much international success. His work as storyteller and artist is often recognized for its interrogation of themes related to identity, gender, and spirituality. Matteo Cantiello is the lead investigator for the Stars in Plasma Astrophysics group at the Flatiron Institute in New York City. The group's stated goal is to enhance our understanding of the physics of stars, their explosive deaths, and the compact remnants they leave behind. Plasma is often described as the fourth and most abundant state of matter in our universe. It is considered the most energetic and dynamic of the four classical states of matter and is most commonly found in stars, including the sun, but can also be created in laboratory conditions such as in neon signs or plasma TVs. Hello, Rahim and Matteo. Thank you for coming on the show.
No problem. A pleasure.
My pleasure.
Yeah.
So it's rare that I hear from an artist who wants to come on the show to talk about plasma physics. So what's the story with your fascination with plasma?
Well, I'm interested in I don't know if it means anything saying like that, but liminal states. So all kind of ambivalence I can encounter in the universe. So the work on the frequencies that you make by being a musician, and in my personal quest for music, the spirituality and the questioning of the real, and actually the deepening of your identity. And when you dive enough into music, it kind of becomes if you allow me the metaphor, a plasma. Please. A bit in itself, because it's a portal-like practice that kind of introduced me to lots more complexity of my understanding of the real. And so I've always been interested a bit in physics, actually. Somehow, like I love to read about quantum physics. I was very interested young, actually, about the life and death of stars themselves, because I feel like it bears such mystery as well. Mm-hmm. It feels like the real scientists that work on science matters actually question more and more. It's almost I wouldn't say it's a spiritual practice. I can't speak for your behalf, but it's more introducing you to mysteries than actual answers. So I always think it's interesting to get there to the real mysteries of life.
Well, that preempts one of the things I was going to ask you. Does it exist as metaphor to you? Especially because I've heard you talk about your interest in the immaterial, the invisible. And you're quoted promoting your last album saying you're addicted to angels. Am I getting that right?
Did I say it like that, Charming? Not wrong, actually.
Yeah.
Yes. Introduced to angels because of life events also, but truly music has always been kind of like a mysterious practice for me. That questioned the invisible, because I couldn't understand where music was coming from. Mm-hmm. When it was existing in my head first. I mean, it's the first big question. Sorry, it makes me a bit panicky when I talk about music and spirituality, because it's an ongoing questioning. Yeah, I like the sacredness of the quest for high frequencies, if I can say it like that.
Yeah, high frequencies as in high vibration.
Yes. Yes.
Mm-hmm.
Enfin, yeah.
And then, is this not irregular for you to hear about plasma as referred to as being compared to the immaterial?
It's a beautiful metaphor, and I think that I resonate a lot to some of the things Rahim said. First, I want to start by reflecting on the fact that you talk about plasma and something that you relate to as an experience being an artist. You mentioned like becoming an artist is somehow feels like becoming plasma. And I like that because the word plasma ultimately comes from the Greek word for something that can bend shape, that changes its own shape, like jelly. In that sense, it feels like that's also the work of an artist to constantly redefine itself. And I think in general, plasma is really the state of matter that has gone to a transition, and it's going to extending its properties and changing the way it behaves. And we know about phase transitions in physics. We're all familiar with moving from liquid to solid phase and the other way around. In the case of ice, we see that all the time. It's actually a fairly complicated thing, but ultimately it's telling something about how molecules of water, in that case, rearrange themselves, and the rearrangement really change the properties of what we observe at large scales. And plasma is another type of transition, and it's usually we're not very familiar with it because it happens in regions of the universe where more extreme phenomena occur, where usually temperatures are higher, which is not a place where people want to hang. So there's a little bit of a bias for us not being present in a region where plasma is abundant, but plasma is abundant in the universe. And of course, we talk about stars, which are made of plasma. And what is a plasma? Ultimately, it's a gas that has been exposed, for example, to high temperatures, so that the collision within the gas, for example, lead to electrons being unbound from the atomic or molecular states of the gas itself. And so all of a sudden, instead of having something which is made of molecules that are floating around, you have molecules plus electrons. And that makes the plasma charged. And that changes everything for the plasma, because being charged, having electrons floating around, and positive also charges floating around, because if you extract electron from an atom, you're going to make the atom being positively charged. It makes it act differently. It reacts to things like magnetic fields. And all of a sudden, there are this collective behavior that happen very smoothly through the plasma, just because the plasma is feeling these forces, the electromagnetic forces, in a way that is different than what it will feel if it was not ionized, if it was just a normal gas. And so the study of plasma is really the complicated study of all these interactions that happen inside this ionized gas between matter and fields, mostly electromagnetic fields.
Is it, en fait, what fascinates me is that is it a detector, almost like a portal for detecting fields of energies, or what kind of matter does it become? Because it seems like almost like a super matter that's charged, but also detecting other or reacting to energy fields. And what can it create? Like, can it bend time?
I see. Okay, so you're asking about, in a sense, once you charge a gas, all of a sudden it can reveal the presence of magnetic fields. So it's kind of like now, and I think it's beautiful when you look at we can look at some of those, but images from the sun, where you do see this structure at the surface of the sun, which are very geometric. You see those arches, you see those tubes, where the gas really seems to flow. They're
like spits out and jumps back
there's
in.
like invisible highways, literally, at the surface of the sun that channel the gas. And it's like, what is containing that? Well, actually, the plasma is following this invisible line, which are the lines, the field lines of the magnetic field in this case. And it's like visualizing it. The same way that you can visualize a magnetic field with pieces of iron. I don't know if you ever seen this experiment. You have a magnet under a piece of paper and you drop like iron file. The pieces of iron just like aligns following the lines of the magnetic field, and they kind of visualize it. So in a sense, it becomes a detector of something normally you cannot see. The same way that the compass can visualize the direction of the magnetic field of the Earth. So yeah, in a sense, it becomes a little bit of a detector of something that usually you don't see. So like maybe, just to show a little bit better what I was trying to talk about. So these are like images of the sun taken from this telescope, which is called the Solar Dynamic Observer, which is literally orbiting the sun. And it's take these videos every day. Actually, you can go on this website and download the current sun in different frequencies. And every day you can look at what's happening on the sun. And this particular frequency of the light, so it's 171 angstrom, which is like in the ultraviolet, it's visualizing these very hot regions at the surface where the plasma hangs and create this structure. And like if I zoom in, you can definitely see this very geometrical alignment of matter that is flowing through these lines very, very rapidly. Usually this happens near regions where strong magnetic fields is present. Usually those are the sunspots. But yeah, this is really like plasma behavior.
Are the magnetic fields like created by the astral bodies themselves, or is it kind of like a net that holds everything together?
Yeah, that's a great question, actually. So the sun shows the presence of magnetic fields that change over time. You know, the sunspot appear and disappear, and these are like regions where the magnetic field of the sun is emerging and disappearing. There is a cycle of 11 years over which the sun produces more or less magnetic field. Right now we are at the kind of a peak of the cycle. That's why the northern lights are so bright and why there's all this activity and spots on the sun.
Didn't know that. Makes sense.
Yeah. How is this magnetic field produced? We have some ideas, but this is something that's not completely understood. There are a couple of ideas. One is assuming that magnetic field is somehow generated deeper in the sun, in a region where there's a lot of shear, where basically we expect a lot of differential rotation in the plasma that kind of steer the plasma and can somehow turn some of the rotational energy into magnetic energy, produce magnetic field that then buoyantly rise to the surface and appear in these loops and arches.
And how long does it take, do you theorize, to get to the surface?
Well, so very fast. So it's a kind of buoyant time, which means that it's like, imagine this like a buoy emerging from the ocean. So of order of like a few rotational time scale. So the rotational time scale of the sun means how fast it rotates around its axis, which is 30 days. But that's one idea. We're not sure that that's the case. The other idea is that maybe there's another process that it's relying just on the turbulence below the surface, so closer to the surface, due to this very turbulent movement, which is due to the fact that the sun is very hot and is convective close to the surface. So there's a bunch of ideas. Unfortunately, we're not completely sure.
That's fascinating to me a bit, because again, it's like working in your field. En fait, you also work with a lot of unknown factors, and you kind of like work with experience and observation, a bit like music as well.
Yeah, sure. So what you said before about like, you know, we keep asking questions and sometimes we get some answers, but we also get more questions. I think that was John Wheeler said something like, the island of our knowledge keeps growing, but also the shores of our ignorance keep getting longer. Just, you know.
Well, like when this is something that fascinates me about science and art is the unknown unknown. The thing that we don't know about that we don't know about. So like when you were starting this latest record, Hope Core, and you're at the blank canvas, is that your experience, or do you go into it with already some information brewing?
Every time it's a quest, and you kind of set the quest with different parameters, I'd say, because I like the record. I actually don't really choose either. It's a mysterious process once you devote yourself a bit to it. This time I knew I wanted to work on frequencies on my own, absolutely. I was studying a lot of, actually we talked a bit off, Giorgio Moroder personally, From Here to Eternity, this record. The 90s club scene, but I wanted to make a very personal interpretation of all those references. And to dive into the work of properly mixing it myself with a lot of fear and questions, but also an experience that I had from before, from working with great artists that I got the chance to work with, that were also very experimental, even at the top of their game. They kept on, even for mixing and frequency, relying on I think they gave me confidence to work on my own style on this one. Mm-hmm. And also because I wanted both a super quest and a super rawness and fragility, because I feel like this would be an interesting balance. And because of when I listen to Moroder's work sometimes, or Jocelyn Pook, or those artists, they get in the conceptual and they find in the texture some answers that influence the whole production. Sorry, I'm sounding a bit abstract, but I wanted to...
Music is abstract.
Well,
it's abstract to try and I've actually
heard...
on
this one, particularly a bit more. Vangelis also as well. I was listening to a lot of the Blade Runner soundtrack by Vangelis. I wanted also the synth to lead, and my love of synth to lead the way a bit.
Well, this is a good point to bring. I've also heard you say that there's something perfect about the expressing with frequency of music as compared to language, which is imperfect.
Well, but words are fat. I mean, poetry is a bit masochistic in the best way, because it's beautiful, but it's always a bit imperfect, because words are highly personal, no matter how universal we think they are. No, I read recently something really beautiful in that regard as well. It's like melody is the real voice of God. I'm saying it all the time now, because I actually think in the progression of notes and the harmonies, and there is something way vaster than language. On Hopecore also the frequency quest was a bit referenced, but very personal, and I had like great moment of mixing when I felt like I was properly highly meditating. And I worked a lot with I'm obsessed with Angels second round. Archangel Michael was really there for me when I wrote a record called Paranoia, Angels True Love. I was really devoted to that.
It was in the promotion of that I heard you say that you were addicted to. Can you expand?
And on Hopecore it's Metatron.
What you're addicted to?
That I was addicted to is reductive. It's just a way to say that I cannot live without them.
Can I ask you to elaborate on what you mean when you say again when you talk about frequencies, finding a frequency for a project?
Well, I don't think I conceptualize it like that either, because it cannot be just one frequency. But I think you work a whole sound landscape where when I speak about the frequency, it's more like the ones that in the mix, it's the ones that actually feel right.
Right.
And the more I studied music I loved, and that was sometimes a bit vintage, I have to say, the less I was interested in the modern way of mixing music, for example, that can be a bit more... don't start me on sound and capitalism, but I felt the personal style of a lot of artists I adored in their work as mixer producers, like even speaking about Vangelis or Moroder, had some kind of style of personality. And I think actually Hopecore was almost like resisting, with my naivety and my experience, some kind of, this is how you have to mix and do things, which feel a bit more in case today with all the technologification of society, and even some plugins that master your track.
Yes.
In the end, you don't really make personal choices, and you also submit to one approach of frequency and mixing. And when I'm thinking of the frequencies I need, I would say more strangeness in the middle and lows, and way less, aggressive plastic shine everywhere.
Yes. Yeah.
And it's almost a philosophy, and it's almost a way also of receiving music, and all the artists I really love, in a way, infused their own style in the frequency of the music. But there are many frequencies to work on one record. It's as abstract as plasma to say that as well, man.
Well, when you say you feel it, we actually did another episode with an artist named Mac DeMarco and an acoustician, and he was saying how that there is a resonant frequency in each part of our bodies. So when we actually feel something in our chest, or it's like, there's certain parts of your body that resonate with certain frequencies, And what's interesting to me is that when we're talking about light and we're talking about sound, we're still using the same form of measurement, right? which is waves.
Yeah.
And so what's fascinating, I don't know if you knew this about Matteo, but he has actually looked into the songs, the sound of the stars, right? Could you talk a little bit about that?
Yeah. First, I want to touch base on this concept of wave phenomena in the universe, because I think it goes back to what Rahim was saying about melody being, superior to words in a sense, or more fundamental maybe. And I think that's true in a sense, because it's closer to the language of the universe. Words are beautiful, emergent properties of humanity in a sense, came very, very downstream from biology. But actually, sound waves exist in the universe every time that pretty much you perturb a system. So sound wave is ultimately the reaction of material systems in the world, in the universe, to a perturbation. The same way that light is the reaction of the electromagnetic system field to a perturbation. So electromagnetic fields react to perturbation with waves, propagating waves. Space-time reacts to this perturbation of space-time, propagating gravitational waves. So waves turn out to be the way that disturbances in the universe are dissipated to reach back a state of minimal energy equilibrium. The universe wants to get back to a steady, calm equilibrium phase most of the time. And it does this by propagating energy away. And it can do that mechanically with sound waves, or electromagnetically, creating light, or gravitationally with gravitational waves. But at the end of the day, they're all wave-like phenomena. And so, there is this really general language that exists, and it's not been written by us. It's written by the laws of physics of this universe. So, when you think about the harmonic series on a string of a guitar, it emerges because you perturb the system. The system wants to oscillate, but the only oscillation that can be sustained, that are minimizing the energy on the string, are the ones that don't cancel each other. So the one there where the nodes of the string overlap, and that's the overtone, the fundamental, the overtone, second, third, and so they all create the harmonic series that way. It's literally coming out of the constraint of the universe and its tendency to always restore equilibrium states and minimize the energy.
Interesting though, because isn't the universe expanding all the time? That's also something that I've been...
That's what we observed. We observed universe expanding and it potentially accelerating its expansion. This is the 2011 Nobel Prize for Physics that showed the existence of something we call dark energy that seems to accelerate the expansion of the universe.
So dark energy is a real thing that we've observed?
We haven't observed it directly. We have deducted its existence by looking at the equation that determined the evolution of the universe. This is actually an equation that was written down by Einstein. And Einstein at the beginning had this famous term lambda, that it added to maintain the universe in a static equilibrium. But then he wanted to get rid of it. And then they put it back in, and now it seems like you need it. And this term is something that allowed the universe to expand at an accelerating rate. What is that term physically? We don't know. People speculate that might have to do with the quantum fluctuation of the vacuum, things that happen at a very small scale and relate to quantum physics. But going back maybe to stars, which is a little simpler. Well, we can talk about the universe. But if you get into cosmology, I think, I'll have to admit that there's a lot of things that we don't know. I think stars, there's a lot of things we don't know, but there are a few things we know I can talk about.
I get it.
So I think for the stars, one thing that is interesting to think about, that we observe these objects, they're far away, they're made of plasma. Beside the sun, usually when we look at the star, we only see like a point source. And the only thing that we can capture is, with the telescope, is a light as function of time, brightness as function of time. We can also take spectra, will give us the composition, but let's say we only look at the luminosity of the star. And if you go in space and we look at the luminosity of the star as function of time, we realize that most stars actually are not having always the same luminosity, but they fluctuate a little bit. They change the luminosity by a tiny bit as function of time.
And this is not the twinkling that we observe from back here.
This is not. If you look at stars during the night, you'll see that actually they twinkle. There's even a little song about it. But that twinkling is due to the fact that light goes through the atmosphere of the Earth, which is a turbulent system, like air rises and falls all the time because of difference in temperature. There are clouds, there's winds, and that leads to the fact that the light like tremble. The same way that if you look on a hot day over the beach and you look at images far away, they seem to like tremble. That's the same phenomena that induce this twinkling in the stars. So usually you need to get rid of atmosphere, so you go to space. And we started doing this like about, a bit more than 15 years ago now. And so what you'll see that most stars actually, they don't have a fixed luminosity, but they change a little bit. And if you look at that function of time and you realize there's some regularity, it seems like the star is somehow oscillating because that luminosity change kind of tells you something about the fact that the surface of the star is not static, but it's moving up and down a little bit. And regions where the star is compressed are hotter, so they emit more light. And regions that are like cooler, that's because, maybe they're rarefied, they emit less light. And so that's kind of that motion is encoded into the light of the star. So in a sense, by looking at the fluctuation in light, the twinkling from space, we can tell something about how the star is moving at the surface. Now, why the star is moving at the surface? There could be very many reasons, but one reason is that some stars are actually giant musical instruments. They're literally oscillating the same way that you plug a string. It's a one-dimensional oscillation for a musical instrument that is one-dimensional. If you hit a cymbal, you also get oscillations, and it's a two-dimensional object. Star is a three-dimensional object. You can perturb it, and you also start oscillating. And oscillating in a very complicated way. But you can imagine that the same way that you can tell the properties of an instrument by its sound, for example, if you hear a cello or a violin, even if you're not in the same room and you're not seeing them, you know which one is what. And you actually know that the cello is bigger than the violin because the frequency of the sound is lower. It's a bigger instrument, it sounds lower frequency. So you can imagine that stars probably are gonna play very, very low tones, very low frequency sound. In fact, the waves that propagate through the star usually have, depending on the type of stars, but they have, it takes like a long time to go through, but the frequency of the sound that they sustain, it's usually very, very low, like microhertz, meaning that it takes like weeks for the wave.
Oscillation.
Yeah. And so it's like something that we couldn't not hear with a human ear for a couple of reasons. One, because sound doesn't propagate in the vacuum, but that problem is solved by the star itself because the star encodes its own sound, its own movement into the light. So the star is converting its sound already into some sort of like electromagnetic channel, the same way that we're doing now with these microphones. We're transforming sound waves into electric signals. And so that way the sound of the star can propagate via light very fast at the speed of light and much farther. And then we can decode it. And then we can use this oscillation that we extract from the light to tell something about the musical instrument. So we can use it to tell something about how big is the star, what is made of, is there any interesting properties in regions that are inside the star? And that's the big thing, because usually you cannot see inside the star. We just saw a picture of the sun taken from very close to the sun, and even there you just see the surface. Just the sun is like very opaque. And it's very hot inside. So there's no way to send a probe even to our sun, which is so close, inside. The only thing we can do is build models or use the sound that they produce to probe with sound waves the interiors. The same way that we know that the center of this planet, the Earth, is made of solid and liquid iron. and we know, the size of the crust versus the mantle. This is because we use seismology, which is the study of earthquakes, which are sound waves propagating through the Earth. And
is there a connection to be made between that probing and ultrasound?
It's exactly the same thing.
Yeah.
Ultrasound, in a sense, is the same thing of seismology. Seismology, usually you wait for an earthquake happening somewhere on Earth, and then, the wave propagates through the Earth and bounce back and forth, and then we have like seismograph everywhere, in many places around the Earth, and so you can measure the time that waves take to come back. You identify them, and then you look at the path. And the path will depend a little bit on what the wave encounter, what the density and the composition. And you can actually reconstruct the interior structure using the information with the seismograph. The ultrasound is a similar thing. You send sound wave from the probe, and they bounce back and forth within your body. And depending on the density and composition of what they encounter, they come back with different properties, which are analyzed, and they give you an ability to determine what's inside and make an image of something that you're not directly seeing. So it's a very similar thing, yeah.
Are we at a point where you can play for Rahim the transposition of the sound of stars?
I think I saw some of that.
Yeah, totally.
It's terrifying, right?
Yeah.
It's
I know.
There's some are terrifying
Yeah.
because something I didn't say is that a three-dimensional object is not going to be harmonic. Already a two-dimensional object is not. When you play a gong, it doesn't play a note. They play many notes, and it's kind of like, disturbing in a way. You can tune it a little bit by suppressing some frequencies. The star, of course, nobody's doing that. The star is just playing a lot of stuff. So I'm gonna play maybe. So again, one thing I didn't say is that you have to transpose the sound by many octaves to get into the audible range. So this is like, I think it's about, it's like 14 or 15 octaves.
It's actually not as many as I would have thought if we're talking about something the size of the sun.
Yeah, it's going to microhertz to, the audible range, which is 100 of hertz. So yeah, this is the sound of the sun.
proper 70s.
Yeah, I know.
And the interesting thing is I told you that as the sun will expand after it runs out of hydrogen, that phase will become a red giant, get bigger until it changes its sound. So we can look at stars that are more evolved than the sun, but they look like the sun in 5 billion years or 6 billion years. So this is the sun. That's a sun a bit bigger. This is a much bigger sun.
That's I'm about to die.
And then there are the type of stars that do different type of pulsations. This is an AP star. This is a star with a strong magnetic field. Not going to talk too much about this, but it sounds very different. It's another AP star.
Cute.
And this is a white dwarf.
I like that.
Yeah.
Yeah.
It's very metal.
Mm-hmm.
So these are all transposed the exact same amount?
About the same amount, yes.
Yeah.
So the white dwarf is the white dwarf actually, it's funny, what I just made you hear is in a sense is the acoustic history of the sun, of the future sun, because we went from the sun as it is now to a small red giant and a bigger red giant. Forget about AP stars. And then we talk about the white dwarf, which is the way the sun will die. The sun will eventually become a white dwarf, which is basically containing almost all the mass of the sun. And because the sun will be smaller, about half of the mass of the sun, confined into something big as the Earth. So
it kind of shrinks and then...
Yeah, exactly. The core of the sun actually, while the outer region of the sun expand, the core of the sun actually, as it runs out of hydrogen, start contracting and become made of helium, and eventually contracts until it becomes a white dwarf. And then the rest of the sun, the outer regions are kind of like removed and they blown away by wind, literally. And what is left is this thing, and it's not burning any via thermonuclear reaction. The only thing it's doing is cooling down, and it cools for billions of years until it slowly disappears, like a candle getting dimmer and dimmer. And this is the most common stellar death we know of. So there's a lot of white dwarf out there, And many we can see because it's still cooling, but they're still visible. And many have cooled down to temperature we don't see them anymore. And they're, for all purpose, invisible. But they're still there.
There is a saying that we are kind of all made of stars ourselves as humans. So does it mean by extension we are plasma?
Well, yeah, actually. So
that's what I wanted to know.
Yeah, so in a sense, we are the ashes of burning plasma. That's the way to say it, because
that's a great lyric.
That'll do. Yeah.
No, it's true. I mean, and it's not a metaphor or a say. It's really something that we discovered in the last century. It took a lot of physics to figure out, but it's a beautiful understanding of the cycle of life in the cosmos. You know, we focus on the biology, of course, now, but to build biology, you need like complicated atomic structure like carbon, nitrogen, oxygen. And those didn't exist after the Big Bang. Only hydrogen and helium, lithium and beryllium were there. Everything else in the periodic table of elements didn't exist for a reason that I don't have to explain, but has to do with the fact that the Big Bang expanded very rapidly. So there was no time to building this more complicated species. So what happened there? Well, there was a lot of hydrogen and helium, which started forming stars. And the stars, as I told you, to shine, they have to burn something. They burn hydrogen in their cores into helium. And then when they run out of hydrogen, they burn helium into carbon, oxygen, and nitrogen eventually. And then they continue the massive one, then burn into heavier elements like zinc and up to iron, which we have in our blood. So all this material we're made of was long ago forged into the deep, dense, hot interiors of long gone stars made of plasma. It's literally the ash of all this burning that was required to keep the star shining and light up the universe for a long time. So we connect to stars that way. Not only life on Earth exists because of the sun, which is also made of plasma. So all the energies that drive the biology and evolution on this planet, which is of course relying on the ashes of previously existing stars, also need the energy, constant energy production and intake from the sun. And so, so we really, really connect to the stars that way.
Kind of makes me think of, is this the same as that concept, panspermia?
It's different in the sense that panspermia, I think it's dealing with concept closer to the abstraction of biology and less to the concept of the building blocks. But you know, where is the dividing line? So people talk a lot about amino acids and things. So at what point you start talking about the building blocks of life? We think that maybe, you know, water with some amino acid, maybe and some maybe more complicated things came from a comet, and maybe that what, you know,
but
allowed.
That's what panspermia
is.
As I understand it, I mean, this is the concept of life coming from from interstellar regions to form on Earth.
Yeah.
Is that right?
Yeah. That the idea is that the first building blocks, instead of being formed here, they came already built to some point, some extent.
Just plug and play.
Yeah, or which you know, it's an interesting idea. I don't think there is any clear proof that that's the case versus life initiated here and can initiate somewhere else. So the question is like, is life so common that can, every time that you have water and temperature, which is like in the right range, and you know, we have all these elements floating around, eventually there's a chance that the Lego bricks get put together in the right combination, that you start building something that has advantageous features that allow it to thrive and replicate and evolve. We don't know. It could be that instead, you know, maybe life only started here and it's the only place. I don't think that's the case, but we will know soon, I think.
Would be set. Wait, how soon?
Yeah.
Do you know?
Yeah.
No, I
Tomorrow.
wish. No, I think that of course, you know, I don't have the answer, but I think my understanding and my looking at the data from the Earth, it looks like life on Earth started pretty quickly. So the Earth is about 4.6 billion years old. There is fossil evidence that microscopic organism started being abundant already 500 million years after the Earth formation. And remind, at the beginning, the Earth was too hot of a place to sustain life. So I think as soon as things cool down to a temperature was favorable and water was in liquid form and abundant, I think that life started emerging, which I think it tells us that with the right ingredients, life finds a way.
Yes.
Of course, I cannot prove that that's the case, but that's what seems like. Given if it was very rare, it would have taken much longer time. In fact, life is stayed in that simple form for quite some time, and it took about 2 billion years to get to more complicated structure like multicellular organism and eventually animals. So maybe the bottleneck is going from unicellular bacterial life into multicellular complex and life and animals. But I don't know. Why I said maybe we'll know soon, there's a bunch of missions. So the reason why we don't know is that we only have one example, which is the Earth. Okay? If we were to find another place where we can't find fossil of life, where life started there as well, then we cannot be done. We'll be done. And especially if that place is on the solar system. So if we go to one of the moon of Jupiter's, for example, which is a place where we're sending probes, and there is like liquid water under the surface of the ice surface of some of the moon of Jupiter, and the people thinking maybe there could be potential for some life there. So if they find life there, I think it means that at least life is very, very common in the universe. That doesn't mean intelligent life or complex life is, but I think it definitely lowers the bar of entry for life forms. And I think that we might know this within our lifetime because of these probes that have been sent to the moons of Jupiter.
That would be fantastic. I would love to have more information about other possibilities of life. It would be greatly humbling, no, for the humankind. In a good way, say.
Is that something you think about much? The possibility of extraterrestrial intelligence?
Yeah. I would love to have some proof of that over my own lifetime. Our own lifetime. First, because I think it would be reassuring. Again, even ethically, I think it would be less terrifying to not be so alone for now with the star guitar sound. And also because it would be fascinating, because maybe it would take other forms, other intelligences. I think we are good with our own. Franchement, it fascinates me as when we talk about science.
You're saying Shiva? Excuse me, Shiva?
Sorry, what?
Are you saying Shiva?
Franchement, yeah, sorry. Sounds like Shiva, but franchement means honestly.
Oh, honestly, okay, thank you.
Overused French word.
Got it, okay, thank you. I didn't know if you were using that as a substitute for God. I was like, well, we can go down that road.
All name of source could work.
Okay.
The scale of poetry.
Okay. Forgive me.
No,
as you were.
I don't know what I was saying anymore, but I lost. I thought of Shiva now. I see it in my head.
Yeah.
So we get super super esoteric.
No, we're talking about like a possibility of not being alone in the universe and how we feel about it.
I would feel great and intrigued. Yeah, reassuring.
Yeah.
And you?
I think, absolutely. And the episode we released today was with another astrophysicist who's kind of made his current life's work looking for extraterrestrial intelligence. And he said that it's kind of just a matter of money. If we spend enough money, we will find sufficient evidence. It's a controversial topic, but I mean, even like the math would suggest that of all the billions of suns, that there is life out there to support it.
Life out there doesn't mean intelligent life or life that is visiting us or sending probes or interested in coming here. I think that there's a lot of questions about that. And
there is another thesis as well, no? If we take the quantum physics and the observable universes and the limits of our perceptions, I read somewhere recently, but I'm not sure if it's verified, but it's not stupid to consider it, that we might not perceive that they even live superposed above our dimension on another one as of now.
Like in a multiverse concept?
Yeah.
Is that what you mean?
Yeah, probably.
Yeah.
Or maybe more simply, I think something Rahim is thinking too is the fact that maybe when you reach certain technological and elevated conscious level, the channel on which you communicate are maybe occurring at a level of physics that we don't understand. Maybe because it's faster, more, I don't know, maybe it's more energetically friendly, or maybe because you don't want those who are not up there with you to receive the message. And it's an option. I think that given our current understanding of the theory of physics, there's not much space for that. But again, like as we discussed before, there's a lot of things we don't know yet. So I think physicists try to answer the question that you have data for and you can answer. There's a lot of stuff where we're not yet ready. We don't have the tools or the observations, and that's the realm of spirituality.
And are you allowed to make those almost spiritual leaps into a thesis that you get to verify? Is there like any kind of poetic derivativeness in the science field?
Totally. A lot of it's interesting how a lot of concepts or ideas also maybe started as spiritual insights and only later became almost like physical understanding. There's a lot of example of that with Eastern philosophy. And sometimes, it's a little bit more of a metaphor than real. People tend to sometimes take some of this thing and say, oh, look, people have figured out quantum mechanics already for thousands. I don't think it's exactly like that, but it gives you like the insight in what the curiosity and the search for answers takes human thought. And I think that's why I think, like the exercise of creativity, even if it's spent into the spiritual realm, is important. And I think it's part of the human condition. What are you going to do? Are you going to give up on answering questions? That's one way to do it, but it's really hard. People want to know. You want to know what's going to happen, and I think you have to, find some sort of answer. Even if it's not the final one, but at least it gives you tools to move ahead and figure out what's next.
Did you always want to work in that field?
That's a good question. I don't know. I grew up really liking writing and humanistic studies, but then I was very curious about nature of reality as well. And I got interested in physics in high school, and then I decided to go and study physics. I also had interest in the sky and the night sky, but more like as a hobby. And then physics became part of my world and my life. And eventually I decided to go and do a PhD in astrophysics. And then I never looked back.
Yeah, I understand that. I was actually wondering as well, like, en fait, it's kind of never ending because are they even transmitting information we cannot decipher? Is the sound actually a communication? Our stars just yelling at us since the beginning of that. We're telling you this. You have to transcribe it.
Going back to what we can say and what we can do with the data we have, people that look around to ways to search for signals. And I think the search that have been done so far, the famous SETI, search for extraterrestrial intelligence, where people have used radio telescopes, using radio waves to listen for signals coming from out there. And it's a very difficult search because it's the needle in a haystack. There's a lot of frequencies that you can search in. So people have to come up with priorities. So like, where would you send the message if you were an alien civilization wanting to be heard? So people thought about certain specific frequencies that correspond to transition of water. And people that look into that, nothing really conclusive have been found. There have been some signal initially. People say, oh, maybe this is interesting. And then most of the time you figure out it's some astrophysical signal, so something natural that happens.
Transition of water as in from one state of matter to the other?
No, from like one excitation level to another. Yeah.
From what, sorry?
Excitation level.
Excitation?
Yeah.
Like movement inside the water?
No, you remember we were talking about like electrons being excited.
So that's like, a gas going to plasma is an instance of that.
In this case, will be more like exciting one electron from one fundamental state to the excited one, going from like the fundamental to the overtone for the string.
Yeah.
And I think that there then I think, if I remember correctly, the idea is like, okay, you have to come up with something simple that attaches to the concept of life. And as I said, okay, water seems to be an important, very abundant molecule in the universe, and seems to be very important for life, at least as we know it. So let's focus on water. What's the simplest transition that will, also make you understand that you understand the physics of this process? And they came up with that. And I think that's what they've been using at the beginning. They also look at other things. Other thing they've been looking at is, I don't know, sometimes people are looking at, now we have this telescope I was telling you, looking at the light of stars, the brightness is a function of time. So you can imagine, what you modulate that? What if you have laser beams that sometimes send some kind of like message? People look at that. And then people look at the other things, like if we had civilization, they're so advanced that they took over a whole galaxy. Galaxy is a collection of stars and gas, and usually each typical galaxy like the Milky Way has about 100 billion stars, and there are about 100 billion galaxies in the universe, a lot of galaxies out there. So we could say, well, out of all those galaxies, maybe there's one where there's been a civilization that is so much ahead of us that they're developed interstellar travel, they know how to extract energy from their stars, they're so advanced that they basically absorbing most of the energy from most of the stars in the galaxy, because that's how they run their whole civilization. And if you do that, you expect the lights of the galaxy to look a little redder, because you use energy and kind of you degrade the quality of the energy. And so basically you mostly have infrared light coming out. So people that look for this infrared, kind of like imagine it as an exhaust of a civilization into a large collection of galaxies to see if some galaxies maybe they have the signature. And none was found that conclusively show the presence of a civilization of that kind. That doesn't mean, again, that doesn't exist. It could be that civilization never do that, never colonize everything. Maybe they get to a point where they build supercomputers, they upload themselves, and they don't go exploring. They just like create worlds within worlds. So we don't know. It could be many possible different things. But so far we have no direct evidence of any of that, which is kind of like, begging the question, if there's so many places for life to develop, and the universe has been around for 13.7 billion years, we've been on, as a civilization, we've been only around for 10,000 years in terms of technological civilization from the agricultural revolution, let's put it that way. So we've been around for zero time. And we're already starting to, create technology. So you can imagine if we are a billion year ahead, what could we do? There's no sign that anything like that has happened and evolved in a way that will create clear signals that we could detect.
Well, the hippie in me wants to suggest that maybe we reversed evolution and went back to plasma. What do you think?
Yeah, I think that would be a mistake.
Yeah. Well, before we started, I heard that a little birdie told me that you'd said we should all behave more like plasma.
I mean, I wish I had that quality. But since it seems like a state of matter that is highly also malleable, right, subjective to extreme change, I wish I could be. My thoughts are, but it makes me question my physical form. I think if we could just also be more like ambivalent portals, it'd be way more fun.
Subject to that you could change easier, or that you're more conductive, or
kind of everything. Everything related to it.
I like it. It's kind of like makes me feel of Bruce Lee saying, "Be water, my friend." Plasma is actually even better because it's the one property of plasma that we haven't talked about, I think is pretty cool, is that once you have a plasma, the interaction within the plasma or with anything outside the plasma mostly happen in what we call, it's not every plasma, but some plasma in astrophysics are called non-collisional plasmas, meaning that the interactions don't occur because particles like literally collide with each other, which is the typical way we interpret interaction in this room. Like the air constantly bounces with each other, bounce on our skin. We touch. We feel like material touch. Well, plasma doesn't do that. Plasma dances around things all the time because it's charged and interact via these fields, via electromagnetic waves. So every motion is this smooth dance around magnetic field lines. There's really there's no
shape.
90 degrees angles in a plasma. You know, almost never do that. There's only like very elegant spirals and curves and it has to do really with the fact that mostly you're interacting via this long distance range thing. So it's kind of there's an elegance to it.
And it feels like a connector, it feels like a connector portal generation of energy. It feels most like abstract but hyperactive as a force or like as a super matter, quite. It's almost a bit science fiction like of a matter, right?
Yeah.
It's almost like a transcended.
And what you said before, in the sense that, you know, it made me think about it. Yeah, we descend in a way, in a very indirect way, through a very roundabout, complicated way, a story from plasma. So plasma is the ultimate creator, in a sense.
And also it's multidimensional. So I wish we could lock that back into our consciousness.
Right. So the reason I said I don't want to go back to plasma, I think it metaphorically, yes, but I think there's something a plasma cannot have, at least as far as we know. It's just like this beautiful complexity of thoughts and consciousness. You know, it's really, really hard to build in a plasma because it's really hard to. So the plasma live constantly in this state of transmutation and change, but consciousness needed this complex, stable, you know, generational things, and we would not be able to build consciousness, as far as we know, at least, for something so ethereal and ever-changing. And consciousness is the way that the universe reflects on itself and decode this crazy story. So if we weren't conscious, we will not tell the beautiful story of the plasma. And so I think that it all goes back to, you know, trying to maximize information and consciousness in the universe.
Yeah. Well,
Can't stars have a conscience, you think? It's like the artist leaping to the gravest subject.
Do it.
Yeah,
Do we even
consciousness.
know? Can we even understand?
Well, I think the question is, what's the definition of consciousness?
Ouais, voilà. There we are.
Yeah.
Great, let's go.
I think in some definition of consciousness, stars are conscious. Like any system that can live in multiple states is conscious. This is a pump psychic version of this, where, you know, consciousness is a fundamental property of the universe. And so a photodiode has some level of consciousness. Then also a star can be in many different states, can oscillate in different ways. But is a star aware, self-reflecting? No. Is that the definition of? If that's the definition of consciousness, then I don't think it is. But again, people I don't think there's a clear definition of consciousness that people has agreed upon. And also we even if with a precise definition of consciousness, we also don't know, even with that, where consciousness come from. There's only ideas and speculations. There's some emergent theory nowadays, but we're far from being able to answer that question.
Well, before we go, I have one burning question, so to speak. Could we make a sun? Like, we can make a hydrogen bomb, right? And you're saying the sun is hydrogen burning for fuel, right?
Yeah.
Could we conceivably find some ice planet that we want to populate? We say, oh, well, we need a source of energy. Can we make a sun?
Yeah. I don't think we will make a sun, like, you know, replicate what the sun is.
We could put it closer so it could be smaller.
Exactly. So, and that's the concept of nuclear fusion. And we've been trying to do this. There's a lot of projects that have been working on this. Actually, there's a big one in France, ITER, which is this idea of trying to confine plasma at high temperature, in that specific case, into this toroidal shape called a tokamak, and use it to generate power.
Can you describe what that shape looks like?
It's like a torus, basically. So it's like a donut, actually. Yeah.
Oh, okay.
Yeah, it's a donut. So the idea, why you want a donut? You want something where the plasma can circulate, constantly, reach a high temperature, but also be confined. So how do you confine the plasma? With magnetic field. So remember those tubes. Now imagine putting that together as a donut.
Okay.
The problem is that plasma, yes, is gentle, moves gently, but when you get to that temperature that you need to a nuclear fusion, and what's the temperature? It's about 20 million degrees. It's very, very hot, and you have to do this in the lab. Plasma start having particles around. There's a lot of stuff in it, and each particle moving very fast, moving around, it produces also its own magnetic field because of charged particles moving and being accelerated in a torus produce their own magnetic field, which we interact. So that system becomes what we say highly nonlinear, meaning that it's very hard to predict its own evolution, very hard to stabilize, which leads to it's a very difficult system to keep contained. And so it's very hard to extract energy in a continuous manner at this point. There's a lot of study on how to do this, a lot of ideas. There's another configuration of the magnetic field called a stellarator, which is similar to a.
I could have come up with that.
Yeah, it's a very good name. There are other ideas where you use other ways to confine the plasma, but at the end of the day, this is the race to produce clean energy, doing what every star is doing and have been doing for a very long time on Earth in a controlled form. Once we achieve that, we pretty much will have clean energy with incredible yield, basically for free. And the hope is that we'll get to that point. The joke has been this has always been like 30 years ahead. But I see this might happen in a few decades, commercialization. And in the meantime, we need to bridge that gap energetically with something else. Yeah. Hopefully not carbon, fossil fuels, but yeah.
Did you have a question, Rahim, before we finish?
No, I think we did a good... I mean, I have many questions as you have. I think we're good for today. Okay. I mean, basically.
Well, thank you both so much. Be sure to check out Rahim's new record, Hope Core, and stay up to date with his work at rahimredcar.com and christineandthequeens.com. You can read more about Matteo's work on his website, stellarphysics.org. Sing for Science is co-produced by Talkhouse and made possible in part by a grant from the Simons Foundation. Our music is by Panoram, social media manager is Bailey Constas, digital producer is Keenan Cush, and our location engineer was Josh Wilcox at Brooklyn Podcasting Studio. Special thanks to John Tracy, Elizabeth Simolike, and Inga Colson for making today's episode possible. If you like Sing for Science, the best way you can support us is to give us a review, tell a friend about the show, and subscribe on your podcast platform of choice. For more information, please visit singforscience.org and follow us on social media at Sing for Science. Thanks for listening.